All right, we're going to have a look at practice question set number 14 here, starting with question number 1. It says, a student uses a bar magnet to pick up a paper clip. The magnet causes what to happen? Well, in order for anything to happen here, really magnetically, the paper clip must be ferromagnetic, which means it has the potential to become a magnet. Now, it has the potential to become a magnet because it's got domains inside it. So if this is my paper clip, it's got domains pointing in more or less random directions. But when I bring another magnet nearby, a bar magnet nearby, what happens to those domains that are pointing in random directions? They start aligning themselves, at least temporarily, to point in the same direction as the domains in the permanent magnet. So this paper clip becomes a temporary magnet because of the temporary alignment of the domains. So the answer for this one would be C. A student uses a bar magnet to pick up a paper clip. The magnet causes an alignment of the domains in the paper clip, which results in the paper clip becoming a temporary magnet. Question 2. Says, which of the following diagrams best illustrates the magnetic field surrounding a bar magnet? Well, we know the magnetic field goes away from the north and it goes toward the south. So the answer for this one, the only one that works for this one, is going to be C. The shape of them is all correct, but in A, B, and D, the direction is wrong. Question 3. Two bar magnets of equal magnetic strength are placed as shown below. The point P is the same distance from each of the magnets. We want to know, in question number 3, the direction of the magnetic field at point P due to the two bar magnets. What I want you to do is treat each of these as separate bar magnets, treat them independently of one another, pretend that this one's not here for a moment, and let's say that the magnetic field at point P due to the one on the bottom goes this way, away from the north. Now let's pretend the other one's not there. The magnetic field caused by the bar magnet that's shown right now goes to the right, toward the south. So we got a magnetic field that goes away from the north. We got one that goes toward the south, and the combined magnetic field there is going to go, well, about halfway in between, up and to the right. So the answer for this one is going to be D. And lastly, this is a tough question actually, it says the Venn diagram below can be used to compare gravitational fields, electric fields, and magnetic fields. And we can see that we've got all three fields having similarities, all three fields having some differences as well. Now it wants us to match the numbers and the regions in the Venn diagrams with the descriptions given below. The first one, can be directed toward the source. Well, can gravitational fields be directed toward the source? Yeah, they always are. Can magnetic fields be directed toward the source? Yes. If the source is a south pole, then the magnetic field goes toward the south. Can electric fields be directed toward the source? If the source is a negative, then the electric field points toward the source, toward the negative. So that means that all three of those fields can be directed toward the source. That means we're going to fill in the first blank with option number 7. All three of those are encompassed by option number 7 there. What about away from the source? Well, gravity can't be directed away from the source. The electric field can be if we're dealing with a positive source, and the magnetic field can be if we're dealing with a north pole. So we're going to say that magnetism, the magnetic field, and the electric field have something in common, 6, and that is that they can be directed away from the source. They don't have to be, because they can be directed toward the source, but they can be directed away from the source. Is inversely proportional to the distance squared. In other words, related to 1 over r squared, an inverse square relationship. Well, we know that electricity is an inverse square relationship. We know that gravity is as well. And we don't know about magnetism because we never learned an equation that describes magnetism, the magnetic field, the magnetic force. Here's the rule of thumb. If you haven't learned it, it's not the answer. That means that the only ones that could fit here, inversely proportional to the square of the distance squared, would be electricity and gravity, which is option number 5. Electricity and gravity. So we're going to fill in option number 5 right here. In the absence of having learned anything about the relationship with magnetism, it's not the answer. Now, what about is directly proportional to the distance squared? Well, electricity can't be, because it's proportional to the inverse of the distance squared. Same with gravity. And magnetism? Well, we haven't learned that magnetism is directly proportional to the distance squared, so it's not going to be the answer either. Again, in the absence of having learned anything about it, it's not the answer. So we're going to say that none of these are proportional to the distance squared, which means that option 8 is the one that we fill in there. So our answer for this is 7, 6, 5, 8.